So this video is about identities, and a person's identity is just who they are. It doesn't change. It's no matter what happens, they have their identity. In math, it's kind of the same idea. It's an equation that's always true, regardless of what your variable might be. For example, x plus x equals 2x. That's an identity because it's always true, regardless of what we are to put in for x. Like let's say x is 5. 5 plus 5 equals 2 times 5, which is 10. Or 0 plus 0 equals 2 times 0. No matter what I put in for x, this is always true, so it's an identity. Some things that are not identities would be something like 4x equals 5x. That's not always true. It might be, like if x were 0, 4 times 0 is the same as 5 times 0, that would be true. But if x were 1, 4 times 1 is not the same as 5 times 1. So this is an equation, which is fine. It might sometimes be true, but not always. Same thing with like x plus 1 equals 3. That's an equation, and I can solve for x, but it's not always true. In fact, x has to be 2 here. So this is not an identity, it's just an equation. An identity is something like x times x equals x squared. It's almost like you're simplifying these and you get something else. It's just like different versions of writing the same thing. This is an identity. It's always true regardless of what I put in for x. Another non-example would be a squared plus b squared equals c squared. Again, this is a cool theorem. It's the Pythagorean theorem, but it only works if a and b are legs of a right triangle and c is the hypotenuse of a right triangle. If I try to do like just random numbers, 1 squared plus 2 squared equals 3 squared, like that doesn't work. It doesn't always work. So an identity is always true regardless of what the variable might be. So here's a kind of complicated example. This is an ACT prep problem, by the way. Which of these polynomial equations are valid identities? Basically, which could always be true? So what I would recommend is just multiply these out and see if you get to this. If this simplifies to this, then it's always true. Or you could try plugging in some numbers for x and y and see if you get the same thing that you do over here. Either of those are a good way to work this out. So go ahead and pause and see if you can try this one, and then I'm going to go over it. All right, so hopefully you've tried it. On this first one, if I were to multiply this out, I would get 6xy and then negative 9x squared and then negative 4y squared and then another 6xy, because negative 2 times negative 3 is 6 and x times y is xy. All right, this does not simplify to this. I've got some of the same stuff, but a little too much. So this does not give me this, so A doesn't work. Let's try B. 2k times 2k is 4k squared. 2k times negative 5r is negative 10kr. 5r times 2k is positive 10rk. I'm going to put kr just to make them match up. Doesn't matter the order you multiply them in. And 5r times negative 5r is negative 25. R times r is r squared. So does this equal this? It does, because negative 10kr and positive 10kr cancel each other out. And I'm just left with this. So B is an identity because this is actually just the same thing as this. So no matter what I plug in for K or R, I'm gonna get out the same thing. So only B would be the answer there. All right, some common identities that we're going to use are called the difference of squares, the sum of squares, the difference of cubes, the sum of cubes. There are many others, but those are some common ones. So we'll look at those in the next videos.